Good afternoon everyone. I am Tanveer Hussain and today I will present our research Pyramidal Attention for Saliency Detection. Salient object detection extracts meaningful contents from input image and depth by distinguishing between the background and foreground. Considering the input data, existing SOD works are RGB and RGBD based SOD models, where we focus on RGBD SOD. The existing RGBD SOD models take RGB and depth maps as input to generate image saliency. Different from existing RGBD models, our method takes single RGB image as input. Our depth model predicts the depth map associated with the RGB image, and collectively we input the RGB image and predicted depth map to the proposed PASNet SOD model to generate saliency maps. The RGBD models are trained and tested with RGB and depth data, where their practical applicability in real-world environments is questionable. Furthermore, depth data sometimes affect the output performance due to the noise in input depth maps. The hybrid models, in contrast, are trained using RGB and depth data, but the testing phase is functional without depth data dependency. The table shows how the proposed model is different from existing ones and achieves state-of-the-art performance. In this work, we present PASNet, a novel pyramidal attention and transformer-based architecture for SOD. PASNet considers a single RGB image and applies features extraction from the backbone network pyramidal block for encoder features refining, upsampling, and features fusion in the decoder. Initially, the RGB image is processed using two models. Firstly, encoder module produces various level features, where the initial level features are refined via the base of the pyramid. The second model generates depth maps corresponding to each input image, while the depth model's intermediate features are fused with mature RGB encoder features in later stages to enhance its feature representation. The decoder progressively fuses these features and upsamples them as well to finally produce the saliency map. The encoder produces alpha, beta, gamma, and sigma. Alpha and beta are CNN features acquired from intermediate layers of backbone model. Gamma and sigma are transformer features from the sequence of fused alpha, beta, and gamma. These features are input to the proposed pyramidal block that is composed of several multi-scale dense arterial spatial pyramid pooling and multi-headed self-attention modules. The decoder receives alpha, beta, gamma, and sigma features, progressively concatenating from the fusion of shallower to deeper layers. After each concatenation branch, PASNet has residual channel attention block, as represented by theta. Theta captures spatial and channel dependencies between pixel locations and different channels of the input feature maps. The saliency map is obtained by gradually upsampling the features during concatenation. The proposed objective function is a weighted fusion of several loss functions, defined for x and y here. In the equation, epsilon refers to the constant weights assigned to each loss function. Structure loss focuses on global structure optimization instead of aiming at single pixels. SSIM loss helps to compute the similarity very well. Regularization is implied to not encounter the overfitting. Finally, the edge-aware loss makes clear distinctions between objects using disparity gradients. In qualitative evaluation of the proposed results against SOTA, herein we present some challenging images. For example, in the first image, the foreground object is hidden and the proposed method produced near to ground truth results. In the second figure, the background and foreground have similar color and the depth map has poor object boundaries. Therefore, the depth-dependent methods produce coarse results when compared to the proposed model. In the next image from NGUD 2K dataset, the object's fine details such as pillars are correctly predicted by the proposed method. Finally, in this image, the foreground and background have similar color and the depth map does not clearly identify the boundaries. Therefore, SOTA methods fail to perfectly map the saliency map of the foreground salient objects. Quantitatively, the proposed method produced best results on challenging SOD datasets such as DUT RGBD, NGUD, etc. Herein the red color shows best results and blue color indicates second best results. So for most of the methods we achieved the best results when compared to the hybrid deep learning models. To perform a detailed ablation study, we removed the proposed pyramidal block to analyze its effect on the overall performance. The pyramidal attention block reduces the error rates by an average of 4.52% on 4 famous RGBD datasets. Therefore, it can be concluded that the proposed PASNet has better applicability and SOTA results. Consequently, we present a new SOD perspective of generating fine saliency maps without acquiring depth data during training and testing. That's all from my side. Thank you for watching.